Hello and welcome to the Interference Technology webinar, Cost-Effective Use of Close Field Probing in Every Project Stage, Emissions, Immunity, and much more. My name is Belinda Stashukevich, and I'm the editor of Interference Technology. Established in 1970, Interference Technology helps EMI and EMC engineers find solutions to their various testing, design, application, and regulatory issues by publishing articles, news, and other practical content. This webinar today is presented by Keith Armstrong. Keith graduated from Imperial College London in 1972 with a Bachelor of Science in Electrical Engineering, specializing in analog circuit design and electromagnetic field theory. He formed Cherry Clough Consultants Limited in 1990, which provides design services to help achieve compliance with EMC. They currently have 800 satisfied customers in almost all areas where electronics are used. This webinar today is sponsored by Nolato Silicon Technic. Nolato Silicon Technic is a world-leading developer and supplier of EMI shielding solutions made of electrically conductive silicone. The end products are used worldwide by high-tech industries as telecom, automotive, medical, and security. Nolato Silicon Technic's 3 production concepts concern dispensing, molding, and extruding of conductive silicone for EMI shielding solutions under the brands TriShield and CompuShield. If you have an EMI shielding solution, contact Nolato Silicon Technic. This webinar today is the first in a series of 2. However, Keith has had many other successful webinar series in the past year. Hopefully many of you attended them. If not, they are available for viewing on our website, interferencetechnology.com, and we encourage you to check them out. This webinar today will be interactive. You'll be able to ask questions and answer polls, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Now Keith will begin the presentation.
Hello. Nice to be back with you again. So this is what we're doing today. We split the webinar into 2 parts because we can spend an hour each. Today we're doing the first 4 here, introduction up to using close-field probes. I'll be telling you how to make your own close-field probes, broadly speaking what they're useful for, buying them, buying spectrum analyzers to go with them, and some other good stuff. And then in March, which is some time away now, we're going to be talking about many more details of actually using them to do a whole range of things in every life cycle stage of any kind of project. You might be amazed by what we see, or when we get around to that point. Anyway, first of all, close field EMC probing is often called near field probing. It's difficult to do accurately, but it's an excellent qualitative technique, useful for comparing things. For instance, does this connector shield better when you put a gasket in or something like that? We can quickly identify emissions problems when used with a spectrum analyzer or an EMC receiver. So I prefer a spectrum analyzer because they're quicker. And we can use them to quickly reveal weak points for immunity, using them with transient or radio frequency generators. I remember years ago, somebody had a problem with a sort of telephone handset. Do you remember those? Wasn't a wireless one. And was failing some national requirement for immunity at 183 megahertz. And this company had a GTEM cell, and they spent a couple of weeks, 3 or 4 weeks maybe, trying to find the problem. But with one of the probes I'm going to show you later on, just a 1 centimeter loop of unshielded wire, I found the problem and fixed it before coffee break on 1 day. Shows you how powerful it is. I've seen similar things. You can use close-field probes to help design printed circuit boards, shielding, and much else. It's low cost, it's very useful. We can easily make our own close-field probes even from a paperclip. I'll show you a paperclip later on. Or rather a paperclip probe, we all know what a paperclip looks like. We can use them to huge effect, with spectrum analyzers costing as little as £800. That would be about, what, $1,200, $1,300, $1,400 US. Maybe with oscilloscopes that we already have, that helps to be able to do Fourier transforms in your head if you're trying to do that. For instance, a square wave, if you pick it up with a close field probe, on the oscilloscope it looks like a series of sharp spikes with exponential decays. Of course, on a spectrum analyzer it looks like a whole spectrum plot. Neither of them look like a square wave. But if you're used to the effect of, close field probes on when you see them on an oscilloscope, it can be very powerful. When people learn to use close field probes and get a bit of experience with them, they wonder how they ever managed to do without them. Honestly, I could spend the whole hour telling you stories about how I'd fixed problems of various sorts by using close field probing that people had spent weeks actually trying to get to grips with. So we can easily make two kinds of close field probes, in fact 3 kinds. I'll show you a third one in a minute. The basic kinds are the magnetic field probe, which is basically a shorted turn which is shielded from electric fields, sometimes called a loop probe. And we have the electric field probe, which is basically a very short whip antenna. Key thing is the largest probe dimension, the length of the whip or the diameter of the loop, should be less than 1/6 of the wavelength at the highest frequency you want to measure. So for instance, for a gigahertz in air, we're looking at less than 50 millimeters in diameter. If you don't do that, then they start to get a bit resonant, and then you can get some kind of complex behavior from them, but it's best to use them a long way short of their first resonant frequency. Here's an example of a good quality close field magnetic probe, and what we've got here is a loop of microwave semi-rigid, that sort of copper-clad, copper-shielded wire. It's a solid copper shield. It's bendable. And as you can see, we've bent it into a loop and we've fed the 2 ends through this shielded box and soldered the shields to the holes in the box at that point. And in fact, the most difficult thing about making one of these probes is getting them to be bent nicely. If you've got, say, 1/4 inch diameter microwave semi-rigid and you want to bend it to 20 millimeter diameter, for instance, it's quite tricky to get it into a nice shape. And it's also quite tricky to cut the shield. Obviously, if you have a shorted turn of the shield, then you don't pick anything up because it shorts out the magnetic field. We have to break the external shield. And we just have a small gap because we don't want to have much sensitivity to electric field. So we have a small gap there, maybe a millimeter, 1/16 of an inch, something like that. And the difficult thing is cutting that and removing that without catching the center conductor, because if you catch a center conductor with your Stanley knife or something, then it's going to probably crack over time. We've put them into a shielded box. There's a common mode choke in there, and it's just really any old RF ferrite will do, I think, with a number of turns wound bifilar. I haven't shown them wound bifilar here because I can't draw that in PowerPoint, but bifilar means we twist the 2 wires together and then we wind them as if they're one wire. And really we're using this as a balance. That's a balanced to unbalanced converter, because all our spectrum analyzers have unbalanced inputs. Now, this is a balanced probe, so we need a balanced to unbalanced converter. Here's a 50 ohm BNC connected to 50 ohm cable. We could have an SMA or an N-type or any other kind of connector, or you could use 75 ohms, of course, if you've got 75 ohm test gear. And most important thing is safety. We need to suitably insulate the loop, and maybe the box as well, with at least 2 individual layers, each rated for the maximum voltage. We'll say more about that later on. Here's an easier probe. Instead of having 2 ends going to a box, you just have 1 end going in. So it's a sort of an unbalanced, it's not very well balanced probe. Here we've still got the break in the center of the shield, and here we've soldered the center conductor and the shield to the shield of the cable at this point. Some kind of strain relief here. Of course, a shielded box would be a great idea. Some kind of connector, and it would help from having a common mode choke or at least a ferrite toroid on the lead that connects to the spectrum analyzer. Don't forget the insulation. Here's an even easier one. This is the kind I tend to make because it's easy. And this is really an unbalanced probe. We've no break in the center conductor in the central shield, but we just at this end we don't connect the shield, and we connect the center conductor at that point. So this little bit here is a bit sensitive to electric fields, so we make it as small as we can. Suitably insulated, of course, and again a common mode choke or a ferrite toroid would be a good idea. An electric field probe is very simple. It's a piece of microwave semi-rigid. Of course, you can use anything really, coaxial wire, but this is handy because it's stiff. And we just have the center conductor exposed by no more than a sixth of the wavelength at the highest frequency of concern. However, if your highest frequency of concern was, say, 300 megahertz or something, you might end up with something here which is about, 6 or 7 inches long, maybe. And the whip antenna that long tends to pick up all the stuff that's going around in the air. So we tend to make these fairly short, because one of the points about close field probing is that the probes aren't very sensitive. We don't want them to be sensitive because we want to be able to use them outside of a shielded room on our ordinary test benches. If they're sensitive, they pick up what's going around in the environment. We don't really want that. Same as before, again insulated. Very important here, not just for safety, to insulate this tip, because this center conductor is connected directly to the mixer on the spectrum analyzer, which is the most sensitive and most expensive part of the spectrum analyzer. And if you touch that to some live circuit, even maybe 12 volts DC or something, you'll blow up the mixer and have to repair the spectrum analyzer, which can be quite expensive. So very important to have insulation, if for no other reason, around the tip here, so that you can't accidentally touch anything to that center conductor. So that was 2 kinds of close field probe, but there's a third kind, which is basically an amalgam of the 2. It's an unshielded probe. Problems with magnetic field probes is that they won't detect electric fields. Electric field probes won't detect magnetic fields. But sometimes you want to know just what's going on, whatever kind of field it is. So a simple loop of unshielded wire can be very helpful. It'll pick up magnetic and electric fields. And if you don't know the nature of the source, it can help in locating the problem area. Or, and then if you want to, you can go in with your magnetic and electric field probes to refine your analysis, as it were. Here are the ones I've been using for many years. And you can see this is just a 1 centimeter loop, not very precise loop, of enameled wire. And you can see it's got a bit damaged here and there. Not very good idea really to have a damaged probe like that. Here's one which is enameled wire, and it's got some shrink sleeve over the top of it. These are only rated for 60 volts DC. Even this one, in fact, isn't really rated than that. And you notice the connectors I'm using is BNC connectors, with chassis mount connectors, but I'm not using them on a chassis. Just handy for soldering too. So ideally, you might want to insulate all of this, at least up to the point where the cable goes in, or plug a cable in and then dip the whole thing in latex or something. You can get pots of latex rubber from do-it-yourself stores, and you just dip stuff in, let the latex dry, dip it in again, let it dry, dip it in again, let it dry, and build up a number of layers. And you could encapsulate the whole of this thing, for instance, or this one, in a nice insulating rubbery latex. In fact, I don't use those probes anymore because I'm using analyzers with SMA connectors on them now, so I've got some other probes with SMA connectors on. Rectangular probe shapes can be more convenient. We often talk about loop probes, but it doesn't mean they have to be circular. Rectangular probes are handier for testing flat things like printed circuit boards or the seams in shielded boxes and stuff like that. And here's an example of a rectangular probe, and it's a paperclip. There's an example paperclip if you're not familiar with them. They're made of tinned steel, and because they're tinned, they're very easy to solder to. So quite often when I found myself in some customer's premises and it turns out we want to do some close field probing, I didn't bring my probes with me, we'll just cut the end off a BNC cable, expose the conductors like this, and connect a paperclip there. Of course, I've shown it without any insulation. Normally we'd put some sleeving over it, but I've just shown it without any insulation here, so you can see that it is just a paperclip. And with probes like these, I've saved people tens, hundreds of thousands of dollars just with a bent piece of paperclip. Yeah, there's no limit really to what you can do with close field probes. You can be quite experimental with them, quite innovative. One of the common things that's done is to make a multi-turn coil. Now they're more sensitive, but they tend to resonate at lower frequencies. But if all you want to measure is, say, the third harmonic of the power line, say 180 hertz in the US, there's nothing to stop you getting a circular former, maybe even a foot in diameter, and winding 100 turns around it. Perfectly good, very sensitive coil for picking up very low frequency magnetic fields. I've seen people wind tiny cone-shaped coils on the sharpened points of pencils. I have to use very fine wire, sort of 40 gauge wire or something, enameled wire obviously, and then put a blob of epoxy on it to hold it still. But you need a magnifying glass just to see the damn things. So these are for measuring microwave frequencies. The trouble with a very small coil like that is that they're very insensitive. So it helps have a multi-turn winding to get a bit more sensitivity. Some people take half a turn of an RF suppression ferrite and put a turn or two, or maybe a dozen around it. The ferrite acts as an antenna for magnetic fields, and you can get commercial products based on this principle, sometimes called surface current probes. And here's an example. This is just a crude sketch of the a 6-turn coil around it. You see this is flat. You can put this on a flat surface, and you can use these for measuring where the current flows. For instance, when you're doing ESD testing on a case and you want to find out where the current flows, you can move these around the case, and in that case you connect them to an oscilloscope rather than a spectrum analyzer, a very fast oscilloscope, and have a look and see where the currents are flowing. It's quite striking. I've used commercial versions of surface current probes to great effect. One time on a synchrotron, that's a 70 meter diameter accelerator, with a beam of electrons going at 99.9999% of the speed of light. It's a big installation with maybe 200 control cabinets and things like that. And to find out where currents are flowing around the vacuum tube, use a surface current probe. Okay, it's time for some poll questions. Over to Belinda.
Thanks, Keith. Attendees, please answer the following questions. Question 1. Close field probing is A, good for comparative measurements, B, good for absolute measurements. We'll give you about 10 seconds to answer the question. We're getting answers in. Most everybody's voted with A, which is the correct answer. We'll go to the next one. Close field probes can help with A, identifying the causes of emissions test failures, B, identifying the causes of immunity test failures, or C, both of the foregoing plus help with EMC design. We'll give you a few more seconds. And an overwhelming majority said C, which is correct. And we'll go to a third question. Close field probes, A, can only pick up either magnetic or electric fields, or B, can be designed to pick up both the foregoing at the same time. Excuse the time got cut off at the end. Give you a few seconds. And the majority, with 86%, said B, which was correct. Back to you, Keith.
Thanks, Belinda. Now we've discussed making your own probes, and but you can also buy them, of course. A number of suppliers of them. Some of them have built-in amplifiers, or they're weak for other reasons. Maybe they're made with very fine wire, and so they mustn't be used for immunity testing. And they won't work, and they will be damaged. You can even get some probes that are calibrated in dB microamps per meter or dB microvolts per meter, but the trouble with close field probes is that calibration will only be correct for a specific orientation and a specific situation, like a long thin wire or something like that. So I wouldn't trust those measurements in any other situation. I'd need to know exactly what the situation was before I was able to use those calibrations. Here's some from Eronia with a DC to 9 gigahertz preamplifier. Here's some from Rapace Instruments in the UK, and these are just very traditional loop probe and an E-field probe, and very well insulated, as you can see, very thickly insulated. Now, just because they're traditional doesn't mean there's anything wrong with them. I used traditional talking about something the other day, and people assumed I meant that they were, old-fashioned and useless. Not the case. Perfectly good probes, and these are all that I use anyway. Here's some from ETS Lindgren with, again, an optional preamplifier. I think that's a mini circuits block there. Langer have a huge range of probes covering 100 kilohertz, 6 gigahertz. This is just some of them. And they've got little tiny probes, like these little very, very tiny ones here. These can measure the, I believe, measure the fields around the pin of a surface mount integrated circuit. That's why they're so small. I don't know if they have a little magnetic core in the tip or something like that. Here's the good old-fashioned Hewlett-Packard door wedge probes with their own amplifier. People have been using these for years. You can get these on eBay. They must have sold hundreds of thousands of these, and a lot of people never use them, so they end up on eBay. There's a low-frequency current magnetic field probe and a high-frequency magnetic field probe, and they're very, very well shielded, to the point where we're testing somebody's product once, and it was failing the emissions test, but these Hewlett-Packard probes with their amplifier couldn't find any problems with the thing in the test chamber. So I got out my 1 centimeter loop and waved it around, unshielded enameled wire loop, and found the problem straight away because it was an E-field problem. And these, of course, don't see E-field, and Hewlett-Packard don't sell E-field probes, or they didn't in those days. We have to call them Agilent now, of course. But they're still excellent probes, very sensitive, as long as you're aware that they won't pick up any E-fields. Here's the current Agilent set that they sell. It looks very much like the Langer RF2 set. I don't know whether it's just a Langer set that's been badged. Here's a set of probes from Tezek, which used to be called Chase. You may remember them as Chase. And these have got amplifiers actually built in to the probe, so there's a power supply for them, but the amplifier isn't separate like we've seen so far. It's actually in the tips of the probes. Here's some Hamag probes. It has a thing in here called a high impedance probe, and I need to look that up because I don't really know what they mean, what that's for. Obviously it's for something. Here's some ComPower probes for electric and magnetic fields in a very nice teak presentation box by the looks of things. Here's the best photograph I've got of the Regal probes. So I said the price there, £250. That's British pounds, obviously. Here's a thing. This isn't really a close field probe in the sense that we're talking about them, but it's a non-contact current probe. I think it's a Hall effect device in the tip or something, specifically for measuring the current in printed circuit board traces. Presumably they have to be traces on the surface of the board and not buried inside. It'll measure currents from 10 milliamps to 20 amps peak to peak, from DC to 5 megahertz. So that looks like a handy piece of kit. For many years I've been using the Tektronix clip-on current probes, but they only work on wires. You have to clip them over a wire, and it's very useful. It's very helpful to know where the current's going. It often doesn't go where you think it's going, so measuring current is very handy. A variety of low-cost spectrum analyzers are available, which you can use with close field probes or current probes, which we're going to talk about in a minute, to check conducted and radiated emissions and do design, diagnoses and assessments. There are expensive models with a variety of sophisticated functions, including the CISPA quasi-peak and average detectors, or RMS as well, and there are medium and low-cost models available to over 6 gigahertz. So here's a few examples. These are ones that I've used and have found to be very effective. Here's a good old Agilent E7400A, originally sold in the mid-90s as a Hewlett-Packard E7400A series. It's a very nice portable instrument with a color LCD screen. They're light and they're handy and they're rugged, mains powered, and they've been around for a long time, so you can get them for a low price on eBay and places like that. They, see how old they are, they have a floppy disk drive slot there, no USB, no Ethernet. They've got GPIB on the back, of course. But what I find with these spectrum analyzers is, because they've got on-screen status displays, I just use a digital camera and photograph the screen. It works very well. Here's a Roden Schwartz a variety, FSH4, 8, 13 or 20, covering from either 9 or 100 kilohertz to 3.6 or up to 20 gigahertz. You can get these E7400s, by the way, to cover from 9 kilohertz to 1.5 gigahertz, or all the way up to 26 gigahertz. These Roden Schwartz ones are very, very sexy looking units. They're about the size of a 10-inch tablet PC or something, quite large, and fit in a pocket if it's a very large pocket. They've got quasi-peak detectors, just like the Hewlett-Packard has here. And one of the things with having, hang on, let's put these up here. There's an Agilent, a very modern Agilent one. I don't think this has quasi-peak detectors. It's just a spectrum analyzer, but that's usually perfectly fine. One of the things with using Agilent or Hewlett-Packard or Roden Schwartz equipment is that screenshots have their logos on and the printouts have their logos on, and it helps to impress people with the quality of your work if you show them something with a Hewlett-Packard or Agilent or Roden Schwartz logo on it. Don't underestimate the effect of the logo. One of the things I've been using just lately is a Thurlby Thandar. You can get this, and you've never heard of them, of course. Thurlby Thandar's a British company, but these are sold through various distributors. It's basically a Palm TX Pocket PC in a housing that converts it into a spectrum analyzer. But you've got all the ordinary Palm TX functions in there as well, you know, with the Wi-Fi and the Bluetooth and all the rest of it. So you can use it as your pocket PC, and when you want to do spectrum analysis, just plug it in here. there's two models. There's a 0.1 meg to 1.3 gigs, and there's a 1 meg to 2.7 gigs. And this really is pocket-sized and battery-powered, and very helpful. It's also very low cost. It's under 1,000 British pounds, or under 1,000 euros, or under 1,500 US dollars. And as you can see, it's got two traces, a reference trace and a live trace. It's got two markers. You can do delta marker, all the rest of it. And it has memories. It has a USB connection. I use my little Thurlby Thandar here for all my demonstrations and also for visits to customers. And I use it with a Palm piece of third-party software that remotes it to my laptop. So the display comes up on the whole laptop screen, and the control buttons are remoted to my laptop screen as well. But just today, in fact, I unwrapped this, which is a Regal DSA815. You may not be familiar with Regal, but it's a Chinese manufacturer, and they've copied the look and feel of the old Hewlett-Packard analyzers. The 9 kilohertz to 1.5 gigahertz unit is essentially the same price as this little Thurlby Thandar here. Of course, it's mains powered and it's not battery operated, and it's bigger, it doesn't fit in your pocket. But on the other hand, it's got four, well, so it looks like 3 here, but I think there are 4 traces on it. Oh, there's 3 traces and 4 markers, that's right. It's more sensitive, it's got a lower noise floor, it goes down to 9 kilohertz rather than 100 kilohertz, and it's got quasi-peak and average detectors in, which the Thurlby Thandar doesn't have. However, you have to pay extra for the quasi-peak detector. You also can pay for the tracking generator, and you can pay for advanced measurement control software. They all add to the price, of course, but even so, it's a very good price for what seems to be, I'll let you know, because I'm just starting to play with it now, what looks like a very useful little box. We need to talk about current probes and pin probes. Now, these aren't close field probes, but we can use them at the same sort of, for the same sort of purposes that we use close field probes. So it's worth looking at them. Here's an example of a clamp-on current probe, sometimes called a current monitoring probe. You can also buy current injection probes used for bulk current injection testing. Very, very handy techniques. And you can get these probes that go down to 20 hertz or up to over 1 gigahertz, though you can't get one which covers the whole range in one go. Fisher Communications are make a load of these. Very handy, very nice units. The principle is, there's the conductor carrying the current. We put a ferrite toroid around it, which has a number of turns on it, which you take to our spectrum analyzer. Now, this shows a solid ferrite, and of course with a solid ferrite, you have to poke the wire through. If the wire's got a great big connector on the end, you might not be able to get it through. So these split probes, which clip on, are very helpful for testing things like that. And what they do is they measure the radio frequency current in the cable. If you place them around the whole cable, they measure the common mode current, which is the one that causes most of the radiated emissions. If you can get into the cable and put the probe around an individual conductor, you measure the differential mode current. And that's usually the wanted signal or power current and some radio frequency noise. And most of the radio frequency noise will be the share of the common mode currents flowing in that particular conductor. So these can be very handy. Here's an example of my homemade current probe, and it's just a radio frequency suppressor. It's a 32mm Stewart ferrite type 28 suppression choke clipped onto the ribbon cable that I'm measuring here, and here's my single turn current probe, shielded current probe. Now because I'm using this in connection with the ferrite, it doesn't matter that the shape of this can change because it's flexible, you see. And being flexible, it's not a good idea for making, as a close field probe, it's not a good idea to have a flexible loop because it might change shape between measurements, and that's no good. But here, it doesn't matter if that area changes because the ferrite dominates its performance. When you take coaxial wire and try and solder the center conductor to the braid, it usually melts the braid, melts the insulation under the braid. So I'm using this with a Kitagawa screen bonding clip. It's a plastic clip, but it's copper, has copper layer on the inside. You can't really see it. I'm using that to clip onto the braid there so that I can make a good 360-degree connection without actually damaging the cable at this point. There's the cable on the test, which is passed through the ferrite cylinder along with the loop of the shorted turn of coax. This is just the 50 ohm through line terminator because I was using it, or I have used it, with oscilloscopes with 1 meg ohm inputs. So you need to have a 50 ohm termination on the end, whether you're using it with an oscilloscope or, well, if you have a spectrum analyzer, of course, it has a 50 ohm input or a 75 ohm input already. Always make sure, by the way, if you're using 75 ohm analyzers, to use 75 ohm connectors. As you push a 50 ohm BNC into a 75 ohm connector, you'll damage it. You won't be obvious that it's damaged, but you'll get a measurement errors. But with a 1 meg impedance oscilloscope, we need a 50 ohm termination. If you don't have a 50 ohm termination on the line, then it picks up all sorts of environmental noise, which is what we don't want. But the current probe like this, if you measure a common mode current which exceeds 2.5 microamps between the frequency range of 30 and 230 megs, then the product could fail the Class B radiated emissions caused by that cable alone when it's tested on a 10-meter open area test site or an indoor semi-anechoic test site. For Class B, between 230 megs and a gig, it'll be 5.6 microamps. Now these are for CISPA 22, Class A and Class B, but they're very similar to the FCC, Class A and Class B. For Class A, it's 7.9 microamps and 17.7 microamps respectively. In order to use one of these, you can either, to measure currents, you can either buy a probe, which will come with a calibration chart, and it'll give you the output voltage in, dB microvolts versus the current it's measuring, or you can calibrate your own one, like the one on the previous picture. It's very easy to calibrate your own probe. If you've got a signal generator that covers the frequency range that you want, you just make a short loop at the output of the signal generator with a 50 ohm resistor in series. Now that should be a 50 ohm radio frequency resistor, not a wire wound one or something like that, but a good high frequency resistor. And you just set the signal generator to a particular voltage and just sweep through the frequency range, and at various points, say 100 kilohertz, 200 kilohertz, 1 megahertz, 3 megahertz, 10 megahertz, 30 megahertz, and so on. Just plot what voltage you get out of the probe on your spectrum analyzer, with the 50 ohm termination, of course, against the frequency. And since you know the voltage the signal generator is putting out, and that means you know the current into the 50 ohm resistor, so you end up with a calibration chart for your probe. What I found when I tried this is that a single turn through an RF ferrite like that typically has a transfer function of about minus 6 dBs. So what I ought to do is put 2 turns around here and make it at least 1-to-1. By the way, I tried this once upon a time. I tried it with this ferrite, with a smaller ferrite, and with a great big ferrite that weighs about a kilogram, a couple of pounds. And the they all seem to give pretty much the same results over the, above 150 kilohertz, which quite surprised me. It doesn't seem critical. This is a very powerful technique, and in certain people's laboratories, certain customers' laboratories, where using a close field probe, the probe was just swamped, even though it's a close field probe, was swamped by the noise that was going on from other people's work and the lighting system and the Ethernet and all the rest of it. Using a close field probe allowed us to see the noise much better. I mean, using a current probe, homemade current probe, was a lot more sensitive, gave us a lot more signal to noise ratio. So I find them very useful. Then we have pin probes. Again, they're not really close field probes, and we can measure the voltage noise on the wanted signal or inject RF currents or voltages directly into IC and semiconductor pins. And it's really just like the E-field probe we had, except we are bringing the semiconductor out now through a small value capacitor, like 10 picofarads or something. The idea is that the capacitor has such a high impedance that if you at low frequencies, that if you touch this probe to some DC power supply or something, or maybe even to the mains voltage, you won't blow up the analyzer. And but at radio frequencies, it's got a low enough impedance so you get some sensitivity out of it. You can inject through this, you can pick up through this. It's not really, as I say, it's not really a close field probe, but it is a very handy probe for certain occasions. Most important issues when using a close field probe is not to damage the spectrum analyzer or the equipment being probed. Sometimes I've been probing products which are custom-made products costing about £500,000 British pounds, that's about $1 million US dollars. There's only one being made, and if my probe damages it, then I get a big bill. So that's important not to damage the equipment being probed. So be careful not to touch any conductors with a part of the probe, maybe even the connector part that you could see on the ones I showed earlier. It's a good idea to have lots of insulation, even if it's just wrapping insulating tape around something. The next thing, which is noticed second in the list, as far as the customers are concerned, they can always get more EMC engineers, but the loss of a prototype might set them back a bit longer. So the next thing is to not electrocute yourself or other people. So it's important to only use probes that are insulated to withstand the maximum possible voltage of the circuits to be probed. On 110, 120, 230 volt mains, the maximum voltage is over 3 kilovolts due to surges. If you want to be really careful, you would go for 6 kilovolts. So, and there are standards that cover this. Standards for insulating probes would be the relevant parts of 61010 Part 1 and 61010-31. In the US, there are UL versions of these, or ANSI UL versions of these. In other countries, like in Europe, there's EN versions of these. But these are the basic IEC standards on which the national standards are based. Now the important thing, oh, and also if they have any damage to insulation, then get them repaired or get them replaced. Don't use them. If you're going to use probes like I showed before, not very well insulated ones, then make sure that only you use them. This is very important because if you electrocute yourself, then you only have yourself to blame. Although your employer, if you're employed by somebody, they could get into trouble for allowing you to use inappropriately unsafe equipment. So if you're concerned about your employer getting into legal difficulties, then always buy probes and make sure that you see the test results which show they really are compliant with these standards. If you're an independent consultant like me and you go and kill yourself, well, it's not a big deal. It's annoying for the family you leave behind, but I've got these probes which aren't very well insulated, which is a bit naughty of me really, but I have to make sure that nobody else can ever use them. I don't lend them to anybody, and they can't get hold of them and use them, maybe when I'm having a tea break or something. So, because if I allow anybody to use those probes and they get damaged, they get injured by them, then I can be legally liable, and even to the extent of having my home sold off, my car sold off, and just be left on the streets in my underwear, okay, owning nothing. This has happened to people, so don't take that risk. Probes, as I said before, are sensitive to near field or close field signals. They tend to ignore ambient noise, although they seem to pick up cell phones pretty well. It makes it easier to identify EMC problems. You have to hold them very close to something to operate, in order for them to see anything useful. And we usually use them to probe seams and apertures in shields, cables and connectors, PCB traces, ICs, transistors, heatsinks. One of the very good uses of probes, close field probes, which I'll tell you next time in March, is to determine how noisy certain microprocessors or FPGAs are before committing to designing with one. You know, most integrated circuit manufacturers don't tell you what the EMC performance of their integrated circuits are, and it's not unusual to find amongst competing products that their emissions are 40 dBs different. That's 40 dBs different. Obviously you want to design with the one that's 40 dBs quieter, but how would you know? With a close field probe you can tell which is the quieter one within a minute, within 60 seconds. That's how long it takes. So you'll find some regions, some parts of some types of probes are more sensitive than others. This is more typical of ones you make yourself, at least I found it that way. So it's important to use a particular probe the same way each time, otherwise you get non-comparable results. Magnetic field probes are polarized. They pick up, or if using for immunity, emit magnetic fields which are more most strongly when the fields are perpendicular to the plane of the loop. So when the fields, you know, the Fleming's right-hand rule or whatever, when the lines of flux are passing through the loop. And this can be very helpful if you've got some magnetic fields being generated from somewhere and it's not clear where. By orienting the probe, or you can find out what's causing them. Often modern products are very complex, and you may have several different candidates for the source of the noise, but by orienting the probe you can zoom in, you can home in on the one that's causing it. But close field probes are all different, and it's difficult to make comparisons between results of different designs of close field probes. And there's certainly no direct comparison between close field probe results and the results of proper EMC testing according to IC or CISPA standards. However, if we keep using just a few probes, our favorite probes, with specific items of test equipment, a certain spectrum analyzer, a certain signal generator and so on, or transient generator, then, and we test equipment that also gets tested for full compliance EMC, you know, depending on the standards, could be military, automotive, or commercial, industrial, medical standards, whatever. It doesn't matter whether the thing's passed or failed the test. The point is that we got the test results, and we can compare them with what we got when we waved our probe around. And so we soon get familiar with how the probe's results compare with proper EMC testing. And that's the end of the first part. Unusually, I finished about 10 minutes early, which is very strange. Anyway, so we've got plenty of time for the questions, and we also have some poll questions too to do.
Yes, we do. We have a few more for the audience. Here's another question. Closed field probes are easy to make yourself, available from several suppliers, or both of the foregoing. We'll give you a few seconds to answer. Pretty much everybody answered C, which is correct. Here's another one. Current probes that clamp around a cable are measure common mode noise currents, measure differential mode currents, or can be calibrated to predict the cable's radiated emissions. And the majority said A, but this one is actually A and C, so A or C. So pretty much almost everybody got it right. And then another last question. Using closed field probing can accurately predict radiated emissions or cannot accurately predict radiated emissions. And we're getting more answers. The majority picked B, which is true. Thank you so much, Keith. We'd like to have a call for final questions from our audience. Please enter any last questions you may have in the navigation pane. We've received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, interferencetechnology.com, and Keith's website, www.cherryclough.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Keith, here's a question for you. I've seen formulas in a textbook for the emissions from very small current loops and very tiny dipole antennas, which include near field and far field terms. Can I measure with close field probes and use these formulas to predict far field emissions in a test lab?
It's an interesting question, and the answer is no, you can't, unless your product consists of, say, one infinitely thin wire, which is infinitely long, over an infinite ground plane. Most people make products which are slightly more complicated than that, and so you can't use these formulae. The academics like to do this sort of thing. Maxwell's equations look fairly simple, at least they do in certain ways of writing them down. They look fairly simple if you get away from the curls and grabs and that sort of thing. And but in real life, applying them, because they're all sort of interactive, they all interact with each other, applying them rapidly becomes very, very complex indeed. Even the most expensive three-dimensional field solvers that you can buy that cost maybe $500,000 a seat don't solve Maxwell's equations. They solve simplified versions of Maxwell's equations. But academics like to show off by saying, well, imagine we have an infinitely thin wire, which is infinitely long over an infinite ground plane. We can write, and we assume, and we look at an infinitely small region of it, you know, a bit of calculus. We can write this formula, which is fair enough, you know, but it doesn't actually tell you very much, except it tells you that there are complex near-field terms and there are some far-field terms. When you come to try and do that for a real product, you find that the complexity very soon overwhelms you. Some of the simulator manufacturers have been trying to use close field probes as inputs to their simulators. So you can take a printed circuit board, probe around it, usually with a robot or something, you know, on a grid, and then say what it's going to do in the far field. But as far as I know, although several people are trying it, it's not been done yet. So in brief, the answer is no. You can't use these simple formulae.
Okay, here's another good question. I make my own close field probes and don't bother to insulate them according to safety standards. Is this okay?
Well, no. I mean, I know I do it, and I shouldn't. I should know better. Well, I do know better. As I said, if you're going to have uninsulated close field probes, or not very well insulated close field probes, then it's best to lock them up somewhere and only use them yourself. And whatever you do, let anybody else ever use them, not even your best friend. Okay? But as I said before, if you're working for an employer and you make your own probes and use them and electrocute yourself or burn the building down or something, which is quite, it's possible, your employer could find themselves legally liable for not training you properly in safety for the work that you're doing. So the best thing to do is to insulate them properly. Get hold of those standards 61010-1 and 61010-031 and apply properly all the appropriate clauses, or else just buy the probes. But when you buy them, make sure that they are actually compliant with those parts of those standards.
Okay, here's another question. Can I use close field probe results as a technical basis for declaring compliance with the European Union's EMC directive?
That's an interesting question. Well, they're all interesting questions, but yes, you can. Now, a lot of people think that in order to comply with the EMC directive in Europe, you have to pass the tests that you've listed on the Declaration of Conformity. But that's not the case. You have to be careful on your Declaration of Conformity to say, I have applied the following test standards. And you list things like EN 55022 or whatever, But nobody knows what the word applied means, not strictly speaking. Now, applied could mean that you've used some other technical method. I mean, for instance, if you've got something like a digital watch that's running off a tiny little coin cell for so many years and it's only consuming microamps, there's no way in the world that even if it emits all that power the microamps is drawing at one particular frequency, it still won't be above the emissions limit. So you can use a technical argument in that sort of situation. And really what you're saying when you declare conformity to the EMC directive, you list the standards and you're saying, really what you're saying legally is, I reckon that if you test, I have confidence that if you test my product to these standards, then it'll pass. It doesn't mean that you have actually tested them and that they passed. Okay. And when you get very familiar with close field probing, especially when you compare it all the time with proper test results, you can get a good feel for it. And if you probe a new product and you see that in the normal way of probing, we're going to go into this more in March, the normal way that you probe things, its emissions are the same or less than things that pass the EMC tests when they're tested properly, then that can be a good basis for saying, yes, this particular test, we can say that we've applied it. And you can save an awful lot of money that way. Certainly a lot of UK companies do this sort of thing. And the thing is, you're supposed to have a technical documentation file, legally required for technical documentation file, that says why it is you reckon that your product passes. If you've got test lab results, then it's the test reports. If you've waved a close field probe around or done some calculations based on the battery power or something, then you can put those in there. But the thing is that nobody has any right to see that document unless it's an official, like a government official, who's following up a complaint. In order to cross national boundaries, in order to be sold in the European Union, all you have to have is the CE marking on the product and the declaration of conformity. You don't have to make your technical documentation file available to anybody. So nobody can tell just from the declaration of conformity on what basis you decided that your product passed the tests. So yes, now I mean I've elaborated on that quite a bit because a lot of people, especially in America, seem to think that you have to, in order to put your CE mark on, you have to do the EMC tests and you have to pass them, but it's not true. And the test labs will be unhappy with me saying that, but on the other hand, the manufacturers will hopefully be happy. So yes, it's possible if you do it, if you do it properly, if you do it carefully, it's possible to use close field probing to avoid having to test a certain of the tests that you have to comply with for the EMC directive.
Thank you, Keith. We have received so many great questions that we will try to address in the future. Keith, thank you again for your time and expertise. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website. We will also send a link to all participants shortly. Thank you for attending.
Thank you.